get started with the Learning to Run a Power Network Challenge session. My name is Jochen Kremer. I'm assistant professor here at TU Delft and co-director of the Delft AI Energy Lab. And it's my pleasure today to announce the winners of this challenge, which we have run in the last 3 months. Oh, hope nothing serious happened. Okay, we need the slides, I think. Just a second. I asked some questions maybe before. Who knows what a power grid is? Great. That's what I assumed. Who has been to a control room? Okay, that's maybe half or 70%, but not everyone. Who knows what reinforcement learning is? Also many. That's great. We have really experts here. Who knows about what topological reconfigurations are? Okay, that's great. We have really a fantastic audience. Okay, I think we are good to go. Ah, okay. Sorry for the short delay. Okay. Now, so what are we going to do in this next 1 hour or so? So I introduce a little bit on behalf of RTE, who is the original the institute or the system operator who has created the Learning to Run a Power challenge, the Learning to Run a Power Network challenge in the last decade. Now we have brought this for the first time here to TU Delft, and I will introduce this challenge a little bit and the history. Then we have 2 transmission system operators here today, represented Elia and Tenet, where we will dive into connected topics on managing congestion in the grid, and also realizing the Learning to Run a Power Network challenge in Elia, concluding from a project they have undertaken recently. Then the most exciting part is really to conclude on the challenge we run, announcing the winners. So we have 3 winners, and we will shortly show a pitch. They have recorded video. Unfortunately, they could not be present here today, as they are from US, China, and India. But we have pitches recorded. We show them to you, and then we have some industry interaction with the 2 panelists. And the speakers, or the winners, also dialed in online to answer questions if you have any. So let me introduce the team behind the organization of the Learning to Run a Power Network Challenge, and that's also really to say thank you to Ali and Gert, who have done fantastic work, and also Benjamin from RTE supported the challenge throughout. Now, where do we start? So, as we all realize, that is a power system, the European one. It's really a complex and complicated system to operate. It's all interacting and becoming more active, and so on and so forth. And this is undergoing the energy transition, as you all know. We integrate more photovoltaic energy storage in the system, so it's becoming really challenging for system operators to control and operate this grid. And if we just look into the energy transition, where here, for example, the projection of France will be in 2020, 10% of solar and wind power is at the moment in installed capacity, and by 2050 this should increase to 50%. And that renders a lot of challenges. Now, especially the challenge which we are looking into is in the control room, right? So that's also earlier the question, have you been to one? And you see an image here how a typical control room looks like. So system operators, humans, sit there making decisions in real time, and it becomes really challenging as the grid is evolving to AC plus DC grids. We want to avoid to increase the grids with new transmission lines, as it is costly. We undertake the digitalization, and so on and so forth. So that challenge ahead has inspired to create the Learning to Run a Power Network challenge. And the idea was really to realize that AI, especially reinforcement learning, is good in a certain type of or class of problems, which is by learning from the environment through interaction. Right, so there were successful examples in 2013 and 2017 here with simple arcade games, and since then the reinforcement learning algorithms have emerged, and it's really a technology that's now being investigated for lots of different problems, and one of them is then really to operate the grid, right? And here it means that a grid operator may use an agent, so this reinforcement learning agent, to as a support, right? So to give suggestions on what could be operated in a different way to meet an objective, right? Or then we would, in reinforcement learning terms, say to increase the reward, right? And through that interactive behavior, the agent becomes better and better with time. That's the idea, and here control actions would be to change the reconfiguration of the grid, to split in a substation a certain bus, or to adjust certain generator units, redispatch. Now, a possible tool could look like this. So this is the hypervision idea. So it's not only one suggestion which the AI or this reinforcement learning agent would provide, but it could be a list of them, right? And then they could be flagged in a certain way. So ranked by the confidence, how certain the AI is, and other metrics which may be important. Yeah. As we want to make trusted remedial actions, so actions which prevent a power blackout, for example, it's important to have certain suggestions. So the operator, the human, has the option to choose, and the agent is really there as a supporting tool, so not to operate it autonomously. And this is really the inspiration to test these algorithms in an environment which has been created. And this is also the Learning to Run a Power Network challenge. So students, researchers, whoever was interested in the last 3 months was invited to contribute, to develop a specialized agent for the challenge of operating a grid. So you can imagine that there is this environment which is a simulation environment of a grid, of course with certain assumptions, and then the student team or the researchers team, the developers, submit an agent, and the agent is then being assessed by a metric, which is, for example, how long you survive or the grid survives before a power blackout. So that's an example of this challenge. And throughout this challenge, more and more data was revealed. They had different phases on verifying their solution, and so on and so forth. And this has now really been concluded in the last 2 weeks. So now the challenge is over, and that's what we are also celebrating today. Now, here's a short history of this challenge. We are not running this for the first time. I mean, here we at TU Delft, we do run it for the first time. But the challenge really has started in 2019. And since then, different variations of that challenge have been developed mainly by RTE. Right? And in 2020, for example, the challenge had 2 different tracks. So one focused on robustness, the other one on adaptability. Right? I'm not going into too much detail as we are focusing on the challenge which we developed today, but also in parallel, there was a separate challenge in France, in Paris, for startups to develop same procedure, so develop also a solution, software solution to the same problem, but in a more realistic way, right? To bring this one step further to operation. So now here, we focus really on a remake of the WCCI challenge, so these are all conferences. So typically they have been held before a conference as we did it this time. Before the PowerWeb conference, annual conference, we have also run this challenge here. And then you have something to celebrate at the conference. And that's also what the organizers did in the last years. So that was the L2RPN Delft 2023 challenge. Okay, with that, I'm now introducing the first speaker. So it's my pleasure to introduce to you Christian Merz from Elia Group, who will introduce how they developed currently the solutions from learning to run a power network to the real grid, and the challenges the transmission system operator has faced along the way.
Thank you very much. Oops. See? There we go. Okay, hello everyone. I'm Christian. I'm coming from Elia Group. Also, hello everyone who's online. So I'm going to talk a bit about what we have done in the last years on the same topic. First of all, well, why do we need to optimize for grid topology? I think we already discussed this, so this is really brief. Then I will talk about our approach and the use cases we see behind it. Then in the next part, I will talk about the challenges. So this includes, on the one hand, the reinforcement learning part or the solving part. Then, of course, which is a big step, is the data part, so actually connecting and getting the right data to actually simulate this. And then the last one is fast load flow calculation to enable the solving. And then in the end, I will talk about the next steps that we are envisioning and also maybe offering some kind of exchange between different people that work on this topic. Okay, so why do we need to optimize for topology? Well, first, before I jump into that, who is Elia Group? Maybe some of you haven't heard it yet. So we are a transmission system operator of a group of 50 Hertz. So this is the German TSO, and then the Belgian TSO. In addition, we have some other startups, other companies that are connected to it. So we have a consulting service, Rialto, which is a data API service, and WindGrid that is developing wind offshore parts. But today we're going to focus on the actual transmission system operation. All right, so let's actually jump to why do we need to optimize for grid topology. And one of the main points here is that we have a huge increasing redispatch costs. So here you can see actually the redispatch cost that we have in Germany. So redispatch, for everyone who does not know it, means powering up or powering down power plants or renewables because we have congestion in the grid. And this is quite a lot. So we have 4.2 billion euros in 2020. And in addition, we will assume that this might not decrease that much in the future because we still have a lot more new renewables. And if we cannot find good ways on how to direct the electricity in the grid, we will also have a lot of redispatch in the future. So there is a clear need to optimize for grid topology. How did we start? So, well, first of all, there was this question. And this question was a bit later than we had it in RTE, but I think in 2020, 2019, there was the first proof of concept, like, okay, can we find some kind of topological action? Can we optimize for this? So there was a first proof of concept, which was called Advanced Analytics for Topology Optimization, that was being run for like 2 years with some gaps in between. And basically, they were showing, yes, it works. It's also really valuable for the business, but there were some downsides. So most of it was scalability, so not running it only on a small grid, but running it on a really big grid. And also the way that you really find good solutions to it. So basically this now, we are in the next step here in where we're currently at. So we partnered up together with InstaDeep, who is a company that is specialized in reinforcement learning. So we're basically working together with them to actually find a solution that goes one step farther on a realistic grid. So what we're currently looking at, well, first of all, maybe this is a bit different than maybe in academic context. You also have to show somehow first to the business and the people you're working with, what is reinforcement learning, how does this work? This is not what we're going to focus on today. So what we did there, we used a bit of the grid to up network, the Learn to Run a Power Network challenge. We visualized this, showed it to the colleagues to actually understand how this could solve. So basically there we had two different approaches. We had a simple rule-based agent and then a reinforcement learning-based agent. And then we were able to show that with a reinforcement learning based agent, you can find, or you can keep the grid more stable on a longer run with less actions. Then what we're going to focus today on is the requirements to implement a reinforcement learning for actually the real grid. And then, of course, we have some other analysis that we're doing on the side, but this is what we're going to look at. So what are our use cases? So basically, the first thing what audio was presented is, of course, find remedial action. So this means in real-time operations. So basically, something occurs, and you need to find a solution. And then you want to have different options that you can choose. So this is real-time or close to real-time. But what most of, I think what I've understood also from other partners are mostly focusing is the operational planning. So this is the day ahead planning. So you already plan for the next day to think about, okay, how should the grid look like tomorrow? What should be my topological action in the grid that we probably won't run into any problems? And then in addition to this, we have grid development. So grid development looks at 10 years ahead or 20 years ahead. And they're only currently optimizing for redispatch. And they said, well, maybe if we can also optimize for topological actions for future grid scenarios, so whether we want to build this line or that line, we might find a better solution. And some solutions are actually available, which we currently assess as no, this is too expensive because there's a high redispatch according to it. So grid development, maybe just 1 or 2 words to that. So basically what they do is they simulate for different scenarios for a whole year, and then different scenarios of grids, and then they decide on which of the future lines they will build. And then next to this, you have a big European level, TSO, academia, and I'm pretty sure this is not a complete list because, I mean, here at TU Delft, you're working on this. There are other partners that are working this on Coreso, so this is like the European level. They're working on an initiative to find a European optimizer for topological actions. Then the whole RTE, grid to op, learn to run a power network. And then there are different research projects. Here I just named 2, which we are more or less part of, but I'm pretty sure there are more. And then, of course, also Tenet, which we will also collaborate in the next phase together. So what are the 3 challenges that we're mostly facing? So, well, show the potential of reinforcement learning to the business. That's one. Then actually get the real grid data into the environment, which is a big thing. And then what we also discovered, we need to speed up the load flow calculation to actually get results in a decent amount of time. Because we're not talking about a small grid, rather small grid than in grid to ops or learn to run a power network challenge. We're talking about the whole, for example, Belgium grid or the German grid. So you have a lot more elements that you need to optimize for. Let's have a look at the first one. So basically, this already I mentioned quickly. So we used the existing solutions, we adapted them, made some kind of visuals that it will show you how it would then take an action. And then we decided to create a little bit of our own version that is adapted to our needs. Because we are kind of in a rush to present certain things, so we cannot show all of the things. We have the requirements that it's scaled, so we are able to calculate on the whole grid and get results in a decent amount of time. So basically, this is why we created a version which is GPU compatible, so we can actually distribute the calculations and set up an environment for this. Then let's come to the next part, the data part. And this is a really tricky part because, as you might can imagine, as always in artificial intelligence or machine learning, getting the right data is the most difficult part. And basically, our requirements seem rather, I would say, not that much. So we want to have some load and generation data with sufficient critical situations, so we actually can train an agent on this. We want a consistent number of elements, so we don't want from one time step to another time step that, for example, one line is off or not in there anymore. And we're working with Panda powers to actually do all of this calculation. And this is where the problem starts, because we do have, of course, all of the historical data from the last 5-6 years, but they are not consistent. So sometimes elements switch, they're not there anymore, and so on. Then you have artifacts in making the transition from one element to another. So for example, if we convert from the grid operation to Amica to then, let's say, Panda powers, you lose some files, so you find a lot of bugs and problems that come along. So actually getting to this point where you are when you're doing the grid to op challenge and doing all of the nice things to train around reinforcement learning agents, it's actually, yeah, it takes a lot of time to get there. So currently what we have now our grid, which we can simulate. We use the data from grid development, because there we also have a lot of scenarios where we can also simulate data. So this is what we're currently working with. And then actually we come to the load flow calculation. So what we did is we benchmarked some of the existing load flow calculations and also benchmarked, okay, which of the part is pre-processing, which is post-processing, so which can we actually speed up. So there we can see that we have different speed ranges of the different solvers. And currently what we will then do in the next step is, together with Tenet, to transform one of the load flow solvers on a GPU to then actually even speed it up more. So what are our next steps? Basically, this is where we are at the start phase now. So as I said, first 7 weeks will be about the load flow calculation on DC. The next step will be then that we will find or try to find some kind of search-based algorithm and then potentially a reinforcement learning based agent in the next phase. And then if we can prove that we can save redispatch cost, then we want to propose this to the business. Of course, we're already working together with them, but actually that they will take it over and also finance this for the future. So what have we talked about? So we had these 4 points. First, why do we need topology optimization? Second, how did we start? So we had this first proof of concept, then we had the second proof of concept, and now we're moving ahead on also trying to collaborate with others. We have the 3 main challenges. So one is about reinforcement learning, finding the right algorithm. Second is about the data. And third is about the fast load flow calculation. And the last thing, what I want to say is we're happy to collaborate and also work with others on this. We will also open source our code, what we have done so far. So yeah, get in touch. We're happy to exchange. Thank you very much.
That's a really wonderful message, I think, to collaborate on this topic as many move in this direction. Which also brings me to the next speaker, where we have a representative from Tenet here, speaking about the practical challenges in AI development for real-world congestion management. So welcome, Davide Barbieri, and the floor is yours.
Hello. Does this work? All right, so hello everyone. My name is Davide. I joined Tenet in April as a data scientist in the digital and data department. I'm originally by formation a machine learning engineer, so please be kind, for my knowledge regarding power networks. And just because I realized I forgot to put this in the presentation, in case for those of you who don't know, Tenet is basically the transmission system operators here in the Netherlands. So to start, for a small introduction, basically at Tenet we have our own Control Room of the Future program, right? And this was established in summer of 2020. And the reason why this was established is because basically, they did an analysis of possible future problems, right, in the company given the energy transition the country is going through. And they identified that congestion management was the top 2, right, considering the likelihood of causing problems and the possible impact of those problems. So therefore, the Control Room of the Future program was born. And we have several tracks in this program, right? Today we will focus mainly on the congestion management track, which is the one that has the highest priority, but there are others, several stages of development, for instance, forecasting, right? Getting our own forecasting for loads and generations, dynamic select lighting, and so on. And what, the common factor between all of these tracks, right, is first of all, to be able to have state-of-the-art solutions, applied to these problems, and to bring these solutions in-house, right, to sort of not depend from third parties for maintenance and updating these tools. But also, we don't only focus on these products, but also how these products are created, right? A big, important part of this for Control Room of the Future program is the environment itself in which these are developed. So these are a few of the things that we'll see today. The congestion management track, we call it the grid options tool within our program. In case, for those of you who may or may not know, in general, the gist of it, as you heard also before at Tenet, we basically use these load flow simulations to first assess possible risk, right? Possible troubling days, and then we try to determine remedial actions, right? Which keep coming up in all of these presentations. And you already heard the 2 examples of remedial actions that I'm going to show. So I'm not going to explain how they work, but I just want you to understand how they are used in real life, right? Because you see it in the simulation, but what is Tenet, for instance, doing? So yeah, in case of the redispatch action, we do have some tooling which still can have some development done, but there is some tooling to automate and optimize the decision making, right? Well, not fully automate, of course, but to help the system operators take decision on redispatching, right? But as we know, this action is extremely costly. On the other hand, for topological action, right, reconfiguring the topology, currently this is done by, the system operators' human brains. So you saw before in the presentation the picture of the operating room, so the control room. So the operators sit there and they just start thinking of possible topologies, and then they run the simulation, and then they try to interpret, okay, what does this mean? Is this better? Is this worse? Right? All of this is done manually. So as you may or may not know from the Learning to Run Power Network Challenge, the action space, the possibility of topological reconfigurations is immense, right? So it's very difficult to fully exploit the full power of this very cheap remedial action by just doing it manually currently, right? So as also was explained before, right, these things can be done at different time scales. Currently, we're focusing in between the day ahead and intraday, which means, again, a plan for the coming day, right? We basically have a 1 hour time spent, right? And in this 1 hour, we express what topology, what configuration we want the network to be in. But of course, we plan to expand to both higher and lower resolutions of time, right? So considering, planned outages and maintenance of the network, but also moving a bit more towards real time. So that's the current state of this congestion management track. Which is currently being developed. Right now, we are testing it on a subset of the Dutch network. This is the Groningen-Drenthe subnetwork. We chose this one for several reasons, but mainly it reflects a lot of the challenges for which this program was born, right? There are a lot of renewable resources there. The flow is very dynamic. So, if we manage to make it work there, we already solve a few of the problems that we foresee for the larger Dutch network. But of course, this also means that another one of our focuses is not only to scale in terms of the time frame, but also in terms of the network size, right? The scalability of the problem, which was also mentioned before. Again, just to reiterate, the idea of this tool is not to fully automate the process, but in the example, for instance, of the hypervision system from Joachim, basically, currently the idea is exactly that, to suggest a bunch of possible strategies. The system operators still have the last say in what decision to make. But this also brings new challenges, right? So this also means that the solutions need to be trusted and understood by the system operator, which means that user experience, human-machine interaction, all this stuff that sometimes is forgotten about when researching reinforcement learning and or other machine learning algorithm. This is also another challenge that is very important for us, right? Because we have this sort of friction from between a business that just wants the best, optimal, cheapest solution, and the system operator that if they see a neural network just switching to lines over and over every 2 minutes, they're like, well, I don't know what this is doing. Should I trust it? I don't think so. And this is, I think, a nice segue between these sort of problems that we often see in real life that sometimes are not necessarily reflected in these challenges, right? One of them is indeed the human-machine interface part, but even there, the Learning to Run Power Network has a trust component, for instance, right? Then another difference is just, let's say, at the interface level, we, in general, look for solutions that are, just for an entire day already rolled out, while in reinforcement learning, you often have this reactive interaction with the environment, right? Like, okay, now do this, then do that in the next time step. So that's just a difference in terms of interface. Another large difference, practical challenge for us is also the fact that the environment is dynamic. The network is a living, breathing thing, right? Like it changes constantly, and as you may or may not know in general in deep learning, but also in particular in reinforcement learning, having the dynamics of the environment changing over time makes stuff extremely complicated if, right, the underlying distributions of the transitions changes over time. So this is a very realistic problem that we are trying to get ahead of. And last but not least, because this is what we're actually focusing the most right now, is the fact that this is also a multi-objective problem, right? On one end, we want safety, right? We want the elements not to be too overloaded, but at the same time, we also, in practice, we don't want to have too many changes to the topology of the network during one day, right? So sometimes during research, it's nice to find an AI doing some very convoluted solution that like really gets the, for instance, in this case, the load flow, right, of each element very low. But in practice, yeah. In practice, maybe that may mean that every 2 hours we need to change completely the topology, which is just not feasible. And also, some of the other objectives are the user experience part that I mentioned before. I have just a small example here. So this may be, for instance, a possible strategy, right, that says, you know, we have 4 hours in a day, let's say, and those are the maximum loading of the element for each topology. And you see that at time step 2 and time step 3, right, we have the same substation as the coupler open, right? So we basically split it into nodes. And there is a difference because one of the elements basically changes bus, right? It changes on which of the 2 bus bars of the substation it is connected to. So this is nice, right? But yeah, an operator may look at this and then they're like, well, there's this other solution where I actually don't change on which bus the line is connected to, right? I still have to open the coupler from, I don't know, 8 a.m. till 10 a.m. But that's not too big of an issue because I can just preset the topology at the start of the day. I open the coupler, I close it, and couplers are always remote, because that's another thing, right? Not every switch can be remotely operated. So maybe that's a good solution, right? It's a bit worse during those 2 hours in the max loading, but maybe that's acceptable. Maybe there is even a better solution. This is what we call a baseline, where you can just set up the topology at the start of the day and just keep the same topology, right? And again, one of the objectives is worse, but in terms of switching is maybe better. And which one has priority is difficult to say, and it depends, right? Maybe in a normal day, in a normal day you may say, well, we can go with this one, right? It's a bit closer to the load limit of a few elements, but it's fine. But maybe it's Christmas where your predictions may be off by a few gigawatts, and maybe you don't want to take the risk, and you just take the safest option, right? We cannot know a priori which objective is more important. And yeah, this is for when the slides will be shared, right? It's basically just to show that we have in mind also a longer term plan where we take into account all of these factors, plus again the user experience of the operator, right? This is this is a concept from very smart people. You can find the paper here if you are interested in the dot in the horizon, as we call it. So finally, I said that we have 2 things, right? The product, but also how we get to those products, the environment itself, right? And I only spoke about the former, so let me just say 2 words about the latter. So again, in Control Room of the Future, we care a lot about the environment in which we develop these solutions. And mainly what we want to do is really bring research and development close together, right? So close that it's almost blurry, the difference. And what does this mean? It means that research, we try to make it a bit more focused on real-world data, right? All these real-world constraints that we mentioned before. We try to take into account during the research process as well. But at the same time, development needs to consider that every 2-3 months, there is a new paper with some revolutionary stuff about reinforcement learning, right? So you need to keep the code modular, you need to keep it flexible, and you need to be able to quickly incorporate what you are researching, right? And this is made possible by data, the holy grail, as it was mentioned many times before. So this brings a very interesting challenge, because to do this, we ideally will research and develop always on Tennet data, right, if it was for us. But it's very difficult to share those. So our current solution is we're working on a data agnostic platform to be able to, share and compare results on open source data and be able to quickly then test these same models on our own Tennet data. And this is the conclusion, just to show that we're not just saying that we care about research, but we are actively participating in a few projects like Graph Neural Network for grid control, AI for RealNet. This is at the European level. It doesn't have to do only with power networks. And we have several master and PhD students working on graph neural networks, multi-agent reinforcement learning, multi-objective reinforcement learning application to our specific use case. So yeah, hit us up if you have you know, a cool idea. Where it's always welcome. Yeah, and this is just a small bibliography. So that's it.
Yeah, great. Fantastic. That's really great. Thanks a lot for this presentation. I also hear that collaboration is important with academia and industry, and also across disciplines. So that's also where the Learning to Run a Power Network Challenge came actually in, to merge the AI developments and the power system communities, as we have realized they were very separate from each other. That also brings me back to the Learning to Run a Power Network Challenge. So I'm introducing now Ali Rajai, who introduces the winning teams.
Yes, yeah. So basically the question was, so just for everyone, whether we need to have a consistent data, or like the question was about, I was talking about the data sources earlier. So yes, you're right. Of course, we want to have different configuration in the data, and we want to have all kinds of different assumptions or tests being done. But just to actually train the agent or to train the environment, we want to have a consistent set of data so that certain elements don't disappear. They can be set off or turned off or like not connected, but they should be still in the same network. So this is what I was mentioning. And I mean, you were also mentioning about, like, of course, the grid itself is not stable, like it evolves, you have new lines and so on. So also this is like, how do we deal with this in the future? Do you then retrain the whole agent every time? Can the agent maybe adapt to a new grid? So of course, all of these are also questions which we have thought of, but actually not really tackled at this point.
1, 2, 3. Yep. So hello everyone, thanks for joining. I'm Ali Rajai. I'm a PhD student here in TU Delft, working with Johan on the topic of topology optimization. So this whole session is really interesting to me. And I was one of the organizers of the L2RPN Delft 2023. So now we are going to take a look at the winners of the competition. Maybe just a quick like a recap that what was this version of the competition. I think we saw it, or like we heard it from our presenters, that how complicated or how huge this action space could be. So for this competition, we are using the IEEE 118 bus system. For this system, we have a observation space of more than 4,000 measurements from the grid, voltages, currents, and everything, and an action space of more than 70,000. And you can imagine this is only for a small scale system and how it would be in a, for example, RT transmission network with thousands of substations. And we use this energy mix to have more renewables and more uncertainty in our environment. In the competition, we have a Grid2Up package, which is like a gym-like library for reinforcement learning, where participants can take action and get reward. So the actions, as we heard before, is the redispatch actions of generators or battery energy storage systems, or to do a cheap topology action. And you can see, for example, in this figure below that the red line is congested, and in the next step, after 5 minutes, the operator or the AI agent makes a decision to split the bus in the bottom border, and then the congestion is relieved. So that's kind of the whole idea about this competition. Just few statistics maybe about this version. So we saw 90 registrations from around the world, from India, China, US, South America, and we had 12 teams actively participating, submitting, and we saw more than 400 submissions throughout the last 3 months. Yeah, and it got a little bit more competitive towards like the last 2-3 weeks of the competition. With that said, that's what we are all waiting for. So RT has generously sponsored the competition to give 1,500 euros to the first winner and 1,500 to the second and third winner. We will hear a small pitch, a pre-recorded video of the winners of the competition. Unfortunately, none of them could make it in person here today. I know, for example, one of them just got his visa yesterday and he couldn't make it today. So that's unfortunate, but we have them online if everything works. So we watch the pre-recorded videos, and then we have discussions over the pitch, and if you have questions from the panel or the winners. If this thing goes forward, I think I'm stuck here, but I think I can just go on and play the video.
Yep. Great, thanks Ali.
Maybe it helps your neighbor, but not yourself. I mean, I understand Coreso might have put the same weight in everybody, but obviously not you.
Yeah, so in our case, so in the Netherlands, Tenet will be the only TSOs. So most of the issues will be between the interaction between the TSO maybe and the DSOs, right, for lower voltage networks. But even there, there is definitely a lot. There is a bit more collaboration, but as far as I know, there is no plan to have an active, let's say, coordination of these automated systems, right? Because we are developing them, and so maybe both DSO and a TSO suggest a remedial action that may actually solve the problem. One may solve the problem of the other. That's a very interesting problem, but for now, yeah, we're sort of, I don't know, it is for Elia, for instance, but for us, we have our network, and then accesses to other parts of the network that are not our responsibility are just either loads or generators or general injection. So we see it as just, let's say, a little town taking its electricity. We don't really consider what's going on in there. So
maybe I can comment on this. The question is, how do TSO coordinate between each other? So there's a European legislation, and there's CORESO, and there's a RUSC initiative on it. And actually, on the European level, they're also implementing this, a topology optimizer. Currently, they are with costly actions, so we're optimizing on redispatch. So actually, there are different measurements. I think it starts from a week ahead, and then it goes 2 days ahead, 1 week ahead, and so on. And then you always have to say, okay, these are the actions I'm going to take. Then this is going to be fed into the model that optimizes for the whole European Union, or for the whole European grid, not the whole European Union. Then it gets back. So there are several back and forths, and this will probably be the same for topology action, but this will be in the future. So this is probably 26, 25, 26, 27. So currently what's happening, as you just described, everybody's kind of developing their own tool. And this is why I was also mentioning, hey, it would be great to collaborate on these topics because everybody's kind of doing the same thing, doing the same mistakes. So to already have like a local optimizer for themselves, because certain problems can be solved, as you also said, in just the grid itself. But of course, if you especially take certain action that are on the border of the grid, it will have an impact for the other tiers. So how it's done today, of course, the grid operations are communicating between each other. So if you take any action, you actually notify the other operator. But of course, yeah, that's also in the future for the European level.
For the question. Now let's move to the exciting announcement of the winners. So we hear or we listen and observe the first pitch by Tata Consultancy Services, Dr. Mahayank Baranyawal and Aman Singh Chauhan.
Hello everyone, thank you for joining us for this presentation. Our team name is Hybrid Agent and I am Anand Singh Chauhan and I will be presenting alongside my supervisor Dr. Mayank Baranwal from Tata Consultancy Services, Mumbai. Our presentation today will focus on our approach of tackling the L2RPN challenge. We have considered the 4 different kind of remedial actions. The first action is a do nothing action and as the name suggests it does not involve to change the status of elements in the power network. This may be appropriate in some cases when the system is already operating within the normal limits and no further action is needed. The second action is a line action which involves line reconnection and line disconnection. Line can be only acted once its cooldown is over. The third action is a topological reconfiguration action and it changes the status of element at the substation. This can be used to restore the normal operation or to prevent further damage to the system. The fourth action is a generator dispatch action and it involves modifying the production of generators to operate the power system. Additionally, we also have storage actions which involves the change in the level of batteries to charge or discharge to control the power network. The control of power networks can be represented as a Markov decision process, MDP, denoted by the tuple of state, action, transition probability, and reward. The state and action are a finite set of state and action, and PA represent the probability of transitioning from current state to the next state under the influence of action A. In order to train our RL agent, we have used 2 different kind of reward structure. The later one is results in a better performance. So the old reward structure is based on the maximum line row value and it is kind of a hinge loss structure where if the maximum row value is less than 0.95 then it results in the step reward of greater than 1. Otherwise it results in either a negative value or a very small positive value. The final reward structure which we have used to train our RL agent, it depends on identifying the offline line count, which represents the line under the adversarial attack right now. And using this exponential function, we are able to find the step reward. The figure shows the schematic of our proposed RL-based recommender system. It consists of 2 main components, a power grid environment based on grid 2 and a RL agent framework. The power grid environment includes an adversarial agent that uses predetermined rules to launch attacks on the transmission line. The RL framework combines 2 types of agent. The RL agent that provides remedial topological actions to address the overload and heuristic-based agent that activated during normal operation that consist of the line actions, storage and the dispatch actions. So from the environment we get the current state and based on this state either a topological action or in the conjunction with heuristic action a combination of action is suggested. We have the feasibility of power grid simulator which uses the forecasted information of next time step to check the legality of action. The proposed action is implemented on the environment and subsequently the next state is fed into the RL framework again. So this process is repeated for the entire episode. Even with AI guided solution, it is impractical to work with a very large action space of nearly 72,000 topological action. So using the rule-based approaches and through extensive simulations, we identified a much smaller set of 264 actions that appeared to have the most impact on the network control. These action set consist of topological actions, excluding the generator actions, and the RL agent trained on the most commonly occurring these 264 actions. So during training, we compare this topological action with the do nothing action, and if this action is better, then it stored in the buffer, which is used to train our RL agent. The flow chart below is used.
Okay, maybe we make a short pause and I will ask the first question, even though the video has not been completed. So now the part is also to invite the audience to ask questions about these approaches to the two panelists, or also to the earlier presentations of the panelists. So one question I have is about the hybrid agents. So we also saw that in the previous competitions, the combination of an RL agent and then to place some heuristics around to make sure certain parts of the grid are not modified, or to place a threshold or some safety net around these actions has been investigated and developed in the past, also in the previous sessions. We heard earlier a few times the keyword trust. Do you feel this hybridization of an agent and other rule-based around the agents increases the trust to an operator when we would use this in real grid operation?
Yeah, absolutely. From our side, it's an essential aspect of whatever solution we find. And one of the big problem indeed is explainability. That is extremely related to trust. And we have found that in general there is a more positive response when you're able to provide some reasoning with the rule-based approach and just wrap whatever the machine learning part of the solution will be. And in fact, I didn't even forgot to mention this during the presentation, but we do not envision in any scenario currently one size-fits-all solution from our reinforcement learning agent, whatever it may be. It will have to be some kind of ensemble, of other rule-based methods. And for now, what seems most promising is also, for instance, a hierarchical reinforcement learning, in which not every, you basically break down the problem and, for instance, the do nothing action as well, and try to determine when to actually call into action the reinforcement learning or not. Even if every component of this hierarchy of tasks is machine learning, the operators may find it easier, right, to wrap their hands around of, okay, right now we are trying to change the topology in this substation because we determined that it wasn't the case that we shouldn't do nothing, right? Even this simplicity in organizing these multiple approaches already provides some explanation and, like you said, some trust. So that's, we feel like that's extremely important from our side.
Okay. Yeah, just to add to one or two things. So basically, this trust issue has been a lot discussed also internally. And what we proposed is, okay, we'll find some solutions, but actually to validate the solution, you will use the same tools that you use today. So you have maybe, as also you mentioned, and some propositions. Let's say you have 10 options, and then you can validate all of these options with the tools that you're currently using. Because as David was describing, currently what is done is people look at the problem, and then they know by their gut feeling or by history or whatever that you can solve it like this or that. So actually there's also no real base like that, this is why I trust. They always say, okay, let's try this. Then they put it into like some kind of calculation machine. They see, okay, if it's stable, and then they use it. And this is what we will do exactly the same. And for the grid to up run network, what we were thinking about is to actually, for the N-1 criteria, to actually calculate all of the N-1 also during training, and not to only have adversarial attacks to it. So actually to be sure that all of these things would be N-1 proof.
All right, great, thanks. Are we good with video number 2? Okay, some difficulty. Does the audience have some questions for our panelists? Yes.
Thanks. I'm way out of my depth. I'm interested in the implications of downsizing the state space. So it seems like they couldn't actually do a kind of brute force analysis, and clearly there's implications of that. But does how you downsize that space ultimately have important implications for the robustness of the findings?
So what I can say is that we're currently actually investigating this. So in the last slide I showed that part of our focus and our plan for the near future is also, for instance, in multi-agent reinforcement learning. And the reason for that is because, maybe multi-agent, like it wouldn't be like academically a correct classification, but for scalability purposes, indeed, we see these agents each possibly controlling a subset of the network and then interacting with each other. And we're currently trying to investigate exactly this. So how would you break it down? What would an agent be responsible for? Is an agent responsible just for a substation, for a region? How would you let them coordinate? Because there are both local effects, of course. If two substations are close to each other, they directly affect each other, but there are also longer effects, right? Like you change a line, I don't know, in Bulgaria, right? And it causes your phone not to charge here in the Netherlands. So this is something that we are aware of, and we're currently investigating exactly what will be the optimal and the most scalable as well way to break down the grid into multiple components, let's say. And another approach is what I mentioned before, possibly to have this hierarchical approach, right? And sort of determine first, maybe perhaps on what region you will want to perform an action, and then have, policies, or you can consider them as separate agents, telling you what that action should be, for instance, right? So we're currently investigating what will be the most optimal one. I don't really have a concrete answer in that sense.
Another thing to this is that we also talked with the grid operators, and they also mentioned, well, certain things, configuration will actually never be done or never be possible. And if you can actually integrate this into the overall model, it will reduce your action space. And the other thing is, that's why we say, okay, we want to invest into fast load flow calculation to actually calculate as much potential options as possible. So these are the two tracks that we're facing, and everything what has already been said.
All right, further questions? Yes.
Thank you. Everyone, have to press it. Okay. Thanks again for the presentation. I was wondering, because you guys are working now on actually gathering all the data, what do you guys think will be the biggest difference after you've managed to get all the data into kind of the same structure as, for example, the grid-to-up competition? Do you think you're able to work with the same heuristics, the same expert rules, apply the same kind of algorithms the way that you did in the L2RPN competition, or are there going to be things that are largely different or largely the same?
So basically, yes, there, as you, well, grid to op or learn to run power network challenges has some limitation in the overall structure. So for example, the substations, I think they only have 2 bus bars, and there are certain limitations that you won't find in the reality, because every grid has been grown by the history. So basically, even the substation inside one grid are different, and also on the size. And if you then go to some other grid operator, that you will also find something completely different. So this is currently the main problem, like aligning this. And that's why we also decide, okay, we'll just create like some kind of own version for the time being, not maybe for the, well, to be seen how maybe in the future this can maybe go again together. But as we have like certain time pressure and things to achieve, to go more or less with the easiest solution at the moment. But yes, it would be nice if we actually can put it all together in the end in grid to ops or in like a common platform.
And just shortly, in our case, what's expected to be one of the biggest problem when if we wanted to migrate directly from, let's say, grid to op to what we have, is the fact that currently we want plan a day ahead, right? And we do this based on the predicted injection and loads, which currently, right, during training, you get these values, you take them at face value, but in reality, there is a huge offset, especially during, say, holidays and so on, between, so this kind of noise that is present in the real world, but not in the simulation. Also, another problem is the fact that the maximum load of certain lines may change depending on the temperature of the day. So again, it goes back to the concept of the fact that the environment is extremely dynamic. So probably that's going to be one of the biggest things avoiding us go directly from the solution grid to op to our data. Yeah.
Great. Okay. I think also that the videos are nearly there. So we have now watched the short video of the winner number 3. So we go from 3 to 1, right? And now we are excited to hear the second submission. So winner number 2.
Hello everyone, welcome to my presentation of L2RPN Delft 2023. It's great to see you online. My name is Dong Pusen, representing my team ACT Smart from Beihang University. Through this presentation, we not only want to show our results in this competition, but also introduce an efficient IR training framework for power network. All right, let's get started. To handle these challenges, we propose our central idea, accelerating IR training, minimize hardware requirements, and mitigating precision loss. To reduce environment complexity, our approach involves reducing the observation space and reducing action space. To accelerate IR training process, we implement pre-train techniques to reduce IR training time. Furthermore, we optimize computational primitive and improve training parallelism to enhance overall performance. All right, let's start with reducing observation space and action space. The original observation space was quite large, with dimensions of 1,4296. However, some attributes are not useful for substation switch, such as the state of charge. Therefore, we directly remove these irrelevant attributes, resulting in a reduced observation space. For action space, the substation switch actions are more than 70K, but most of them are already used. So we follow 2020 solution to find a great action to minimize the maximum load rate of our lines and add it to action library. In the end, we filter out the less used actions and reserve a set of high-frequency actions. This process enables us to refine the action space, ensuring that we focus on the most relevant and efficient actions during IR training. After making our environment more light, we shift our focus to the training process. The traditional IR training process consists of 2 stages, the optimized stage and the sample stage. In the sample stage, the agent interacts with the power network. environment and to collect knowledge. While in the optimized stage, the collected knowledge is used to update the agent. We observe and record the execution time of both sample and optimized stages. We found that most of the training time was consumed by sample stage. This tells us the importance of the knowledge efficiency and the sampling speed, because they greatly influence the overall training speed. The key to speed up training is to make sample more efficient. Based on the above findings, we propose 3 techniques. First is pre-train. We employed a pre-train approach to get prior knowledge for our IR model. We conducted explorations on 800,000 scenarios. For each observation, we searched for a great action from a reduced action space to minimize the maximum load rate of all lines. We stored the observation and the chosen action. Finally, we get a dataset of 40 gigabytes. This exploration was performed on a 32-core CPU machine with 32 processes for 28 hours. After generating dataset, we processed the dataset by removing duplicate elements. After that, we trained a neural network on a machine with 32-core CPU and 4 V100 GPUs for 13 hours. Now we have completed the pre-train phase. The next step is to fine-tune the model using our algorithms. To enhance our training sample parallelism, we adopted the active-learner paradigm. In this paradigm, multiple samplers collect examples based on their current policies, and these examples are sent to a central optimizer. The optimizer then uses the examples to update the weights of their own policy. The optimizer broadcasts its policy to the samplers, and the samplers update their internal policy. By using this approach, we can effectively parallelize the sample collection. It enables us to make the most of available computational resources and accelerate the learning process. Beyond that, we have also introduced quantization into our training. Before the optimizer broadcasts its policy, we use PyTorch post-training quantization to quantize the full procession policy. The quantization is defined by the following equation. In this equation, A represents the step size for mapping float point numbers to integers. After quantization, the sampler interacts with the power network using low procession policy. In our results, the graph above is the weight distribution before quantization, and the graph below is the weight distribution after quantization. You can see that the quantization still maintains the distribution of weights. Interestingly, the quantized approach obtained more rewards during training. We attribute this improvement to the fact that quantization introduced noise, which the noise could be considered as exploration. This allows the agent to explore unknown states and discover better actions. In our final solution, we have successfully combined distributed training and quantization techniques. Quantization plays a crucial role in accelerating the sampling process. We are also reducing communication and storage overhead. It achieves this by using low procession policies for the samplers. In our final solution, we employed the PPO model, and to handle continuous actions, we use the Optim CVX PY agent from L2RPN baselines. To further improve training efficiency and resource utilization, we leverage the benefits of distributed training and quantization. Okay, that's all. Thanks for all of you guys listening.
You may now think why we clap, because it's a video and he cannot hear us. But that's incorrect, because the speaker actually joined us online. And this is also now the invitation. We have very little time for one single question to the presenter for the second prize, if you have any. Okay, then I have one. Can you hear us? So I saw in this approach also the reduction of action space and the state space. And that may mean to introduce some suboptimality to not anymore get some optimal actions. And I was wondering how the winner number 2 thinks about it, and if there's any metric or any way to compute how big this suboptimality was. Not only based on the score, right? Because we know the second winner has performed very well.
Hello, everyone. Can you hear us? Hello?
Can you hear us?
Oh,
Hello?
yes.
Great. Did you understand my question, or I may repeat the question?
Oh, please repeat it.
Okay, so my question is, you showed action space and the reduction of the action space and the state space, and I wonder how big you think is the suboptimality being introduced to it. So would you say it's significant, or is there any way to quantify these type of reduction? So of course that it becomes computational feasible. How big do you think is the suboptimality? Is there any way to compute or to predict that?
In our solution, we introduce the quantization into the RL training, and the quantization, when we train the RL model, we in the optimized stage, we use the full possession policy to maintain the possession. But in the sample stage, we use the low possession policy. In the because of the low possession policy, we can collect the experiments more faster. So we can accelerate the training and make most of the hardware resources.
Great. Okay, thanks a lot. Thanks again. So we move very quickly to the top winner now. All right. Thanks for the answer, by the way. And we played the top winner now.
Hello, everyone. Today I'll be presenting on the topic Enhancing Enumeration and Optimization Strategies for Power Network Operation, which underlies our solution to the L2RPN Delft 2023 competition. My name is Shaurya Bose, and my team members are Qiling Yang and Yu Zhang. We are all with the Department of Electrical and Computer Engineering at University of California, Santa Cruz. The goal of the competition is to design an agent-based controller which can operate an electric grid for extended periods of time. A snapshot of this year's grid is shown on your screen. The competition is based around the Grid2Op package, which is developed by RTE France for the purpose of simulating grid operations. The goals are as follows. Given a chronic, we aim for the following. First, there should be no danger lines or lines where the flows exceed the thermal limit. Second, there should be no load shedding. Lastly, the costs associated with generator redispatch, renewable curtailment, and battery usage must be minimized. To that end, the following actions are available. We can redispatch fuel generators, we can curtail renewable outputs, we can set battery charge or discharge powers, and we can change bus bars and or line configurations. Each substation is endowed with 2 electrically isolated bus bars, and we can connect any element to either one of them, while the lines may be disconnected or reconnected after cooldown period. There are several challenges, the first being the hybrid's action space with continuous as well as discrete actions. Secondly, the number of discrete actions suffers a combinatorial explosion as the size of the grid grows. Third, the environment is not robust to incorrect actions. For example, disconnecting a wrong line can cause widespread blackouts. And lastly, for initial time steps, The best action is no action, and the agent must know when to snap out of no action into actively controlling the grid. Here are some earlier approaches to L2RPN, and they are built around the concept of a unitary action that is changing the bus bar of an element. For a substation with n elements, there will be 2 raised to power n unitary actions. WCCI 2020 sees a multi-timescale control with the slower timescale outputting full topologies and the faster timescale outputting unitary actions to get there. NeurIPS 2020 sees evolutionary strategies to train a neural net controller to output top K unitary actions. ICAPS 2021 sees a neural net policy and heuristics to choose the best unitary action from a pre-computed list and also discretizing the dispatches. WCCI 2022 sees top 2000 unitary actions figured out from a simulation followed by using the AlphaGo algorithm, while the runners-up use top 300 unitary actions from an unspecified method followed by using the OSQP solver in the CVX framework to optimize continuous variables. Here are the principles of our approach. The best strategy on any time step is as follows. We should reconnect out of service lines as soon as possible. We should choose a unitary topology in a way that extends the episode duration, and we should optimize continuous variables using the OSQP solver in the CVX framework. Second, for an overloaded line, a good unitary action can be found in its neighborhood. Consider figure on the top right, wherein for the overloaded line, the blue nodes are the neighborhood of degree 1, the blue and yellow nodes of degree 2, and all colored nodes are that of degree 3. Third, we should perform n-1 contingency testing, wherein each line is assumed to be disconnected and the best remedial action is found. This is denoted by the figure on the bottom right. Here is our algorithm, which can be found in the GitHub repo at the link at the bottom. It is divided into 2 stages, training and evaluation. During training, for each line, L, and each chronic available in the package, we fast forward k time steps randomly in the future. Should the episode survive the fast forwarding, we disconnect line L, and then we find the best remedial unitary action in a neighborhood of degree 4. The best action, by the way of reducing the maximum relative line flows, is recorded in a lookup table, and depending on the frequency, the lookup tables for each line L are truncated at 350. Now we move on to evaluation, wherein nothing is done if there is no danger lines. Otherwise, all unitary action corresponding to the danger line are simulated. Should there be multiple danger lines, then the number of actions simulated are capped at 350. The best unitary action is selected as the discrete action, while for the continuous actions, the DC power flow model is solved in the CVX framework to reduce the maximum line flow. Some implementation details are as follows. We see that should we implement our training in serial, there will be 4 layers of for loops and the total time will exceed 49 years. To that end, we implement parallelization, wherein the line disconnections are parallelized, while the number of unitary actions are significantly reduced due to searching in a neighborhood. By this way, we reduce our training time to approximately 23 hours. We implement training in a machine with 2 AMD EPYC 64-core processors, with each core having 2 threads and each thread being able to carry out 1 simulation process. The NVIDIA Titan RTX GPU is used for the baseline agent, and the baseline agent consists of not doing anything until the line flows exceed 0.95, and when it does, a neural net agent trained with soft tactic-critic reinforcement learning algorithm is implemented. On your screen, you can see a zoomed-in view of both the proposed agent and baseline acting on the grid. For the proposed agent, we see a larger number of unitary actions being applied, which is denoted by the lines changing color from blue to green and vice versa, which shows that the bus bar to which the line is connected is being changed. Now we see that the baseline agent has terminated its episode, while the proposed agent's episode is still going strong, denoting the robustness of our approach. In summary, our proposed algorithm generates a robust grid controller which can prevent blackouts for an extended period of time. Parallelization and neighborhood search significantly reduce the controller's training time. The future direction of this work are as follows. We want to merge current algorithm with deep architectures in a reinforcement learning framework to improve performance. We also want to generalize the agent to scenarios beyond the setup of L2RPN. With that, we would like to thank you for viewing our presentation.
Great. All right, thank you. And I think also that speaker has joined us online, if I'm not mistaken. Okay, hi. Great. Congratulations for winning the Learning to Run a Power Network Challenge Delft. With that, we are closing the session. Thanks, everyone. Thanks for the speakers. Thanks for joining this session, the audience, and the good questions, and enjoy the rest of the conference.
Thank you.
Small gift. Great. Thank you.